Hey statistics students, this is Unit 10, Lesson 2. This video is going to be at least in 2 parts, possibly 3, depending on how long-winded this gets. We are talking about the testing still, so we're still doing hypothesis testing, but now we're going to be talking about the difference in means. So by that, it's a situation when you would be answering the question, has an average number of hours changed from one year to another, or they did some experiment and did one treatment on average cause people to get better more than the other. So it's whenever you're looking at the average, but you're making comparisons of them. So that's when we're going to be talking about the difference of means here. So we're going to be talking first mu sub 1 minus mu sub 2 for our population means. The observed difference between two sample means, x bar sub 1 and x bar sub 2, could possibly be showing that there is an actual difference in the parameters of mu sub 1 and mu sub 2. It could just be chance variation, sampling variability, random assignment variability that could have happened. So we quantify that by doing a statistic test to see which one is more likely. When we do this, we are going to use the general form of the null hypothesis, stating that mu sub 1 minus mu sub 2 is some hypothesized value. Typically speaking, though, we're mostly going to be interested in when the difference is 0, which means there is no difference. The null hypothesis says these population means are the same. So we will mostly be writing that the null hypothesis is that the first population's average minus the second population average is the number 0. You're sometimes going to see that rearranged and just saying, well, if there's no difference, that means these two means are equal. These are equivalent statements. Typically, I will be writing this one. It means the same as the other one, though. The alternative hypothesis is just going to say what kind of difference we expect. We expect a positive number, we expect a negative number, or you just expect it not to be 0. The conditions for performing this test will be the same as when we constructed the confidence interval for the difference in population means. So we have to check our randomness. The data has to come from 2 independent random samples. That's important to note and to include in your explanation. It could also just be from 2 groups in a randomized experiment. If it's a randomized experiment, you're not drawing from the population without replacement, so you get to skip the 10% condition. But if you're sampling without replacement, then your first sample size needs to be less than 10% your first population size. You have to do this for both groups, so you also need to note that your second sample size is less than your 10% of your second population size. You'll also have to check the normal/large sample condition. For both of your 2 samples, the corresponding population distribution needs to be normal. If you're talking about an experiment, then the corresponding true distribution of response to a treatment would also need to be normal. You're oftentimes not going to know that, so instead you could check to see your sample sizes are large, which means this is again for each sample. So I'm just going to write n has to be at least 30, but that does mean that n sub 1 has to be at least 30 and n sub 2 has to be at least 30. If you don't know the shape of the population and you have a small sample size, remember that's when we graph our sample data and we check for strong skewness or outliers. So example, did this just freeze on me? Example 1, if we want to know if the average number of hours Americans work in a week has changed, this is a question that was associated with or asked on the GSS, the General Social Survey. They asked respondents how many hours they worked each week. Responses from random samples of employed Americans were recorded both in 1975 and 2014, so we have the summary data here. We're trying to see if we have convincing evidence that the true mean number of work hours per week for the employed Americans in these 2 years is different. So I don't care what the difference is, I'm just trying to see if they're different, which is going to inform our hypotheses. So the null hypothesis, again, we're just going to start by saying that if I subtract the population means, I'm going to assume I get 0 until I can prove otherwise. I'm not trying to say whether 1975 was more or less than 2014, so I'm just going to say I'm looking for a difference. I'm looking to see, do we have convincing evidence that it's not 0? And as always, you need to define your variables. Here comes a kid to come in and whine. I apologize in advance. So we are going to be defining what mu sub 1 and mu sub 2 are. So I just realized I used 1 and 2. 1 and 2 would still need to be defined. Personally, I would rather have this defined as mu sub 2014 and mu sub 1975. 2014, 1975. It is a little more meaningful, and I tend to not screw it up as much if I have it defined that way as opposed to with just generic symbols. So then I do need to say that mu sub 2014, this thing is driving me nuts, mu sub 2014 is the true mean hours worked per week by these employed Americans in this year. It's the true mean hours by employed Americans, and this is specifically in 2014, where mu sub 1975 is the true mean hours worked per week by employed Americans, but in 1975. This step annoys me just because it takes so long to write, and you're writing essentially the same thing twice, but you do have to define your variables. We need to check our random condition. The important part to remember on the random condition, you don't just need random samples when you have two samples. They need to be independent random samples. If they're not independent, you're looking, whoa, that's never happened before. You're looking at paired data. If they're not independent, you're likely looking at paired data, which is a completely different process. So they do need to be independent samples. They do need to be random samples. So we have independent random samples specifically of 764 employed Americans in 1975 and 1,501 in 2014. So next I'm going to check my 10% condition. This was not an experiment. I have a population of American workers. We are randomly selecting some of them without replacement. So we technically don't have independence. So we're just going to check to see if it's mathematically the same. So because I put in my order 2014 as my first group, I'm going to keep talking about 2014 first. So the 2014 sample size is 1,501. That's less than 10% of all employed Americans in 2014. That is a reasonable assumption to make. Likewise, it's reasonable to think that 764 is less than 10% of all employed Americans in 1975. We don't know the shape of the distributions of the two different populations in question, but we can just go ahead and look at the sample size. The sample size in 2014 is large. The sample size in 1975 is also more than 30. So because we crossed that threshold, we've met this last condition, we can proceed to actually running our test to see if we have convincing evidence that there's a difference. When we do this, we always standardize our test statistic and find a p-value that is associated with it. You always use the same formula of statistic minus the parameter over your standard error of the statistic. What I want to point out is the parameter is what we are assuming to be true. We are assuming that the null hypothesis is true, so that means this parameter is going to be 0. We don't know sigma, so our standard error of the statistic has to be the one without the sigma. We can't use the standard deviation of the population, can't use the normal formula is what I'm trying to say. So we're not going to be using the normal distribution, we're going to be back on the t-distribution. Our statistic is the difference in our sample means. The parameter is 0. And the standard error of our statistic is the formula with the square root of the first sample's variance over the first sample size plus the second sample's variance over the second sample's size. As long as the normal large sample condition has been met, then we can use the t-distribution to find the p-value associated with this. You have to know your degree of freedom for a t-distribution. So there's the way using technology, essentially, whether that's to find your degree of freedom with that awful formula or to have your calculator find the degree of freedom for you. We'll do that in a second. The other option is just to figure out what's smaller, first sample size minus 1 or second sample size minus 1. Whichever one is smaller becomes your degree of freedom. Now that's the conservative way to do it. It will be good enough, and it used to be the pretty much only best way to do it. We have technology, we don't have to rely on that way. So in that example, still talking about our employed Americans, we already checked and we have the conditions met for a significance test. So now I just want to know first, what is it about the sample results that gives some evidence for the alternative hypothesis? So the data we observed, we can actually find the difference in the sample means. The alternative hypothesis is talking about the difference in the population means. We have data based off our sample. So if I subtract those two sample means, so if I subtract these two, because I've defined 2014 first, I'm going to subtract 41.91 minus 38.97. The difference in the sample means is 2.94. So we have some evidence that the null hypothesis is not true. We have some evidence in favor of the alternative hypothesis, which, remember, the alternative hypothesis said that the population average in 2014 minus the population average in 1975 is some non-zero number. And we have evidence of that because the difference we just got is not zero. Now, that could be something that's really meaningful, or it could just be, hey, you just randomly select these groups of people. If you had a different sample, it wouldn't be that far from zero. So we're going to quantify that with our p-value. We have some evidence. We're looking for convincing evidence. So we need to take that 2.94 and standardize it and find the standardized test statistic. So remember, that's the difference in your sample means, the 2.94 that we just calculated, minus the parameter. So we are assuming that the difference in the population means is zero. We're assuming that's true until proven otherwise. And the standard error of our statistic is the 2014 standard deviation squared over the 2014 sample size plus the 1975 standard deviation squared over that sample size. This often leads to issues with people calculating it, so a lot of students will make mistakes at this point. So I'm going to show you in a second how to use your calculator to get that, but we'll just use 4.88. Let's pretend I took the time to put in my calculator and I got that. So we'll talk about, again, option 1 in a second using technology for this. Let's talk about option 2 first. Option 2 is where you use your degree of freedom of the smaller sample size minus 1. So of those two sample sizes, 764 is smaller. I'd have 763 degrees of freedom, which is not on the t-distribution table. You'd have to round down and you'd use 100. So it'll be a really conservative guess here. But I would be looking at the t-distribution with 763 degrees of freedom. I'm looking at specifically the test statistic of 4.84. Sorry, 4.88. We can find the area to the right of this. So that's going to affect our p-value. Because this is the t-distribution, we can use t-CDF. I'm finding the area to the right of that test statistic. And I'm going to note the degree of freedom that this is using, which was 763. That's not the p-value. That helps us find the p-value. But if you remember way back when I wrote those hypotheses, this is a two-tailed test. So if I stop here, this would be half of my p-value. The other half of the p-value is using the opposite of the test statistic found. Scissors, like. Sorry, talking to Mr. Dresch. So I need to take this TCDF and either before I type it in or after I type it in, double it. So when I put that in my calculator, it is a ridiculously small number. It spits it out in scientific notation. It's times 10 to the negative 6. So I'm going to have 1, 2, 3, 4, 5 zeros. And then 1, 2, 9. That's after I've doubled it, which is very, 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 very unlikely. So I'll talk about the implications of that in a second. I want to show you the other way to find this p-value. So option 1 uses technology. And specifically the function in your calculator you're going to be looking for is the two sample, because we have two samples. We're using a t-distribution and we're running a test, not creating an interval. So when I use my calculator's two sample t-test, let me pull up my camera for this. So when I use the it's so blurry. Good enough. Two sample t-test. Most of us, that's going to be under stat, and we're going to scroll over to the tests. Casio, Inspire people, it might be slightly different. So scroll over to tests. We don't want a regular t-test. We want a 2-sample t-test. I don't have data. I have a bunch of statistics. So I'm just going to type in my statistics, which I already did because it's the second time I've made this stupid video because technology hates me. So I'm putting in my first sample mean. You'll notice that it's the second row of our table because technically I defined my first sample as the 2014. So this is 2014 average, 2014 standard deviation, 2014 sample size. Then you'll see 1975 average, 1975 standard deviation, 1975 sample size. I need to tell my calculator that it's finding the area in both the tails, so it's a 2-tailed test. And then it asks pooled yes or no. Always put no. Technically this, I guess, could show up, but it'll be if you know things that we're not going to know. You'd have to know that the population standard deviations are exactly normal. You'd have to know that your variances are exactly, you're not going to know that. Just put no. And then calculate it. You can see it gets the exact same standardized test statistic that we got, but the degree of freedom is definitely different because they're using that formula that I showed you once and I'm never going to show you again because your calculator will do it for you. You do need to write down that you're using this degree of freedom. You do need to write down that using this degree of freedom, this is the p-value that was calculated. So either method is fine as long as you're clear what you did and what you found using what you did. So I did get a test statistic of 4.88, but the p-value slightly different, not dramatically, but definitely different, 0.0000115. And again, that was with degree of freedom of that number. So a little more accurate because we're using a better degree of freedom, but functionally the same. You'll notice both gave us p-values that are extremely small, far less than 1% of the time this should happen if the null hypothesis is true. So remember, that p-value always gets compared with alpha. So because our p-value of 0.0000, I don't know how many zeros I've said, because the p-value of 0.000115 is in fact less than our alpha value of 0.05, we're basically saying we were assuming the null is true. Assuming there's no difference, the probability of getting this average in these 2 years that were this far apart or even further is so unlikely that it's much more likely that it's just not true that these were equal to start out with. So what that means is first we're going to reject the null hypothesis, and if we've rejected the null hypothesis, then we're saying we have convincing evidence of the alternative. And in context, the alternative is that there's a difference in the true mean hours worked by employed Americans in these 2 different years. So the structure of this test is the same. It's just applying different stuff in the middle of it. So we're going to put together the 4-step process of this